Welcome, everybody, and thank you for your time. I think it's going to be time well spent. And the reason I say that is because I wish I attended more webinars like this. Not just Bayfield webinars, of course, Bayfield webinars is fantastic, but just in general, I wish that during my time as a student, over a decade ago, we had more conversations like this. I don't think a lot of people understand the magnitude of the role of what data science plays in society, and people, or at least me, when I initially started, thought about data science, and all I thought about was, algorithms, the matrix, and the green little numbers, and all of those things. And I think it's a massive misconception, because data science is incredibly broad, and I think grasping, having a bit of a deeper discussion about what it entails would actually, indicate that you've actually been involved with data science much more than you probably think. So welcome. My background is in a bit of data science, a bit of finance, a lot of real estate finance as well. So I spent too much time in university. So here we are, making sure that I can at least transpose some of the knowledge that I've learned, to the next generation, and for anyone willing to listen. I think everything, as with everything, even if you test an hypothesis, if you're trying to solve a problem, it all starts with a question. And this is the fundamental question: what is data science? When you talk about data science, what does it actually mean? What is the principle underlying data science? And I thought about this for a very long time. And the only way that I could conceptualize it for myself back in the day was saying, all right, so it's ultimately using techniques to obtain insights that are hidden. That's how I initially, conceptualized it for myself. And then for this webinar, I wanted to be a bit more poetic. So I said, it's essentially the science of discovering the story that the data is telling you, and then using and applying techniques that gives you value from it, that benefits you. And I think that's really what data science is doing. It's very multifaceted. It's not just one dimensional. And we're going to touch on this a bit more, but ultimately you're trying to figure out, okay, if we have a specific question, and that could be, any type of question, it doesn't matter what industry you're in, you're essentially asking the question, what has happened in the past? And you'll have a historic idea of that. Then you will ask, why did this happen? Will this possibly happen again? And if this happens, can I protect myself, or can I benefit from something like that? And this relates a lot into data science and statistics, just in general. When we start talking about descriptive statistics and diagnostic analytics and predictive analytics, and then prescriptive, where you try to optimize everything. But in principle, when you look at data science as a whole, you've got three component parts. I mean, the one way to sum it up is the analytical computing, because that's really what it is. It's computing and analytics. It's a merge of the two. On the one side, you've got your statistical analysis, which is, a lot to do with the mathematical science of statistics. And on the other side, you've got the computational, the processing power and the techniques that you can use. So I'm sure you're all familiar with this already. Statistical analysis. What's the probability of something happening? What does this distribution look like? What's the standard deviation? Can we test the hypothesis of the likelihood of something being linked to something else? Is there a strong linear relationship between specific variables? Can we identify factors that determine the value of something, like you would in a regression analysis? And you'll make inferences based on that information. So that's the statistical side of it. Now, what makes this very interesting is, even though they're now, you've got computational on the right side and statistics on the left, you sometimes have some computational elements that's already on the front side of statistics, but we'll touch on that a bit later. So it's really a circular flow. But from a computational perspective, data mining, database querying, where do you obtain the information that you do the statistics on? What is the process that you use? What type of tools are out there for you to do that? What type of processes do you use? Is it machine learning? Is it econometrics? Is it what type of programming language do you use? And then, of course, you also have the advent of artificial intelligence, which is very exciting at the moment. And AI has also opened up some other opportunities in terms of cloud computing and what can be done inside the cloud as well already, which kind of nullifies some of the things that we've done in data science in the past because of how the IoT has evolved. But we'll touch a bit more on that a bit later. So in principle, if you need to explain data science simply, it's all about having a conversation with data and trying to figure out, you're a detective. You're trying to figure out what is going on and how can I use this information to produce insights, and how can I use that insights to benefit me or to reduce risk, depending on whatever the outcome is. So another question is why it matters. And I want to, before I even start this, I want you to think, or just come up with a number in your mind. I will reveal it afterwards, but come up with a number in your mind when you think this article by Forbes was published, what year it was published, because that's kind of like the ticker of this conversation that we're going to have here. But the reason that data science matter is because, and this is probably something that you've heard a lot. Data is the oil of the 21st century, because if you think about it, data is at the foundation of everything we do. If you're not even working in finance or even working in real estate finance, if you have some kind of CRM, client relations management systems, you have some form of database where you store information. If you've gone paperless, think of where AI is going now, what it's doing with large language models, as I've pointed out at the top. We're really in a era where data is just significant. And as you can see from some of the statistics from this article, there was more data created in the last 2 years than ever before. I mean, that's such a profound statement if you think about it. It's just bizarre to think how long we've been on this planet and how much data has been generated in the last 2 years to, exceed everything that's been generated prior to that. And then if you think about 1.7 megabytes of new data was created every second for every person on Earth, if that happens every second, that means that's 6 gig of data every single day, every minute. I mean, that's quite that or in an hour. If you, my math is terrible, but if you multiply that, imagine if that's per second, per minute, per hour, per day. I mean, just think about how much hard drive space you have on your computer, and trying to put that into perspective. That's quite remarkable. And the irony is that only a half a percentage point of the data that is actually collected is actually analyzed. It's almost like using the analogy of the ocean. So much of the ocean is not explored yet, and there might be new discoveries of new species and all kinds of things. The same principles here. So many different relationships and ways to quantify information exist. We might now, because of this remarkable volume of data, be able to identify new ways to actually interpret it. Over 6.1 billion smartphone users worldwide. Now, these smartphones that you have in front of you, this collects data in real time. This is also real-time data. Within 5 years, more than 50 billion smart devices will be connected. Now, that's PCs, computers, gaming systems, TVs, smart TVs, everything, tablets, you name it, will be connected. Google uses 1,000 PCs to make sure that they can process a search query within 0.2 seconds. 1,000 PCs. 10% increase in data can provide access to a Fortune 1000 company. Data accessibility, just increasing that with 10%, can add over $65 million in income. And then finally, on the problem side of things, better integration of big data, because healthcare, of course, sequencing, DNA sequencing. Oh, I'm not a specialist, so don't quote me on this, but there's a lot of data points, the same way you would be able to look at the electronics of an aeroplane, how many ticks, how many fuel is burnt per millisecond, etc. You have the same in human biology. A lot of data on human biology is becoming available. So being able to use that, you can save a lot of money. You can advise. I actually have a friend who also read for his PhD at Cambridge at the same time as I was. And he found a company that actually looks at how to look at that type of information to detect potential issues, health issues of people in the future based on, their history and their family history. And it's just remarkable stuff that can be done, where you can save a lot of money. Now, the irony is, I wish I could see who can put up their hand. This is something I would probably ask my students when I teach them in class. But this article was written 10 years ago. 10 years ago. And their estimations, all of this estimations in here, was actually for the year 2020. We're half a decade beyond that already. So it's the magnitude of this is even more. So the reason why it matters is because data is just increasing, and we're going to require more people to actually process this information. Now, you can argue that AI can do a lot of these things, and you'd probably be right. But having now used ChatGPT, Claude, Grok, DeepSeek, all of the sophisticated AI tools, they still get it wrong most of the time. So they're getting better at it, but it's not quite there yet, and we still need to communicate with these tools to actually do the analysis. We need to tell them what to do. That's how it works. So if you would like to learn how to do that, of course, we have a course coming out sometime soon, a prompt engineering course that teaches you exactly how to communicate with AI in a specific way. So it doesn't matter which AI you use, if it's Copilot because it's integrated into your business systems, or ChatGPT or Claude. We give you a wide overview of that. It's a very, very exciting course, and it's very relevant to this for what it's worth. Now, the data science skill set, what do you need to do? A lot of people think you need to go to university and learn how you need to do computer science. That's not correct. I did not study computer science. I wasn't the smartest guy, or let's just say I wasn't very. Let's just say I was more lazy than the average guy, because all I wanted to do is play professional sport, and then luckily I had some injuries, so then I had to actually put my foot down, and I had to do a lot of work. So you don't need a computer science degree to learn how to code. You can teach that yourself. Now you've got embedded AI that can teach you how to code within Anaconda, which is essentially the launch package for Python. Maths and statistics, that's obvious. It comes with the territory. And then domain expertise. If you want to specialize in healthcare, you need to at least understand what type of data is being researched and being collected in healthcare. In real estate, the same story. In finance, what type of data? Is it stock data? Is it bonds data? Is it derivatives? What are we talking about? So it's all about having that like business domain knowledge. We need to understand that. And then finally, communication. And a lot of people miss that. You can be the smartest cookie in the room. If you can't communicate your findings in a way that people can actually understand, in a financial setting, for example, you can't raise capital, because how am I going to convey to someone who's willing to give me billions of pounds to invest on their behalf that the information I have is valid if I don't know how to explain it? So it's really a multifaceted system. Now, this data science pipeline that we have in place, step one, collecting information. That can be structured, unstructured data. It's not like an Excel table where we've got a nice little set with property ID, property price, volumes. It's not very nice. It could be very unstructured. It could be text. It could be image. It could be, sound. It could be transcript data. It could be text, just in general, text files, but also just text in PDF format, for example. And that can be completely unstructured, but you can analyze that and produce a structured data set from it, onto which you can apply statistical techniques and computational analytics to derive that from that. How do you fix errors? Would be the second. It's probably the biggest one out of all of this, is how to clean your data before you use it. Because garbage in, as you can see on the left, is garbage out. That is so important, because at the end of the day, all of those little errors or the assumptions that you make, the lazy assumptions we make, like, no, I'll just use an average, or I'll just use a mean, that affects your outcome dramatically because it compounds over time. Then the exciting part is the EDA, exploratory data analysis, and finding patterns and insights, trends of data. What is the data telling me? What's the conversation I'm having? And then you'll build your model. That can be a variety of things, on the algorithmic side of things, which is mainly mentioned here, but that's also regression and econometric models, simple econometric models as well. And then you deploy the system, when it's out. When it's ready to go. Once you've identified the information that you need, built a model that fits the data well, that produces analytics that's statistically, significant, provides value, then you deploy, then you use it to your benefit. Now, to look at each of these individually, and I want to make sure that we don't run out of too much time, but the data collection side is actually quite straightforward. You typically have programming languages like SQL, where, for example, MySQL, where you usually obtain information from databases, and they're usually very structured. Then you also have APIs. I used to have to go and sit at a Bloomberg terminal to get information. Now I can go into an API to pull information from that, or from a fund provider, or any type of data provider. And web services. Cloud platforms, that's what I wanted to talk about earlier, AWS, Azure. You can now actually process and do computational steps within the cloud even before the data gets to you. So the big data can be processed and produced in a way that can get you in a refined form, which you can then further refine, or you can just use machine learning within the cloud to actually answer the questions that you would have done anyway. So that goes beyond what we're going to talk about today, but that is a possibility and a reality. Data cleaning and preparation, 80% of your time, hands down. How do you handle missing data? Do you use an average? Do you use a mean? What do you do if there's missing data? Imagine house price data, which is monthly, like index data, but you also want to see what the effect of GDP is. GDP is collected quarterly, so you only have quarterly data. So what do you do in the month in between? How do you get the data to match up from a time series perspective? All of those things matter. Outlier detection, kind of, it's almost linked to data normalization to some extent, but sometimes you have data which have significant outliers. And looking at that information, you can say, well, this data point actually doesn't fit this sample. It's an outlier because of X. It doesn't fit the narrative. We can take it out, but obviously only take it out if you should really take it out from an ethics perspective. You don't want to, alter the data to make your answers, look in a certain way. But then you also have data normalization, which scales the data in a way that makes the distribution a bit better. If you're using like an OLS or a OLS or a regression type system. And then feature engineering is like combining variables. Let's say you will multiply the number of bedrooms with the volume, or the number of bedrooms with a number of bathrooms, and you'll correlate that interaction term with the property price. So that's a very simple example, but that's at least a example of what feature engineering involves. And then we've got exploration. We've touched on that already. I won't deal with that more on that, but that's all about uncovering the patterns, or figuring out where there's errors, or what is the answer to this test that we're doing, or a hypothesis, and making sure that we verify that the answers that we're getting is actually statistically valid. It's all about statistical validation, at least at the end of the model stage. And early on during the EDA, you can at least find some link to it does make sense, or it will make sense. So it's almost like a preliminary analysis of the final verdict of what your data is going to tell you. But ultimately, you've got your descriptive statistics, the historical element, asking what has happened, distribution analysis. What does the distribution of this returns look like? Are they skewed to the positive, skewed to the negative? What does it mean for our outcome? Looking at correlation between variables, how highly linked are they? What are the patterns within the time series? If you're running a time series analysis, can we see specific patterns, moving averages, etc.? What does that tell us about the information? And ultimately, you'll put it in a model. That's the final step. Obviously, you roll out is the final step, but then you will put it in a model. Once we've followed this approach, we'll have either a statistical model, an econometric model. It's relatively similar, but or the algorithmic model, which we discussed earlier. The recurring neural networks, those type of things, decision trees, random forest. It's just a couple of examples on here. But once you have the data processed, cleaned, you've done your exploratory analysis, and you decide on a model, then you're ready for rollout. And that's essentially the application of the data science process, which we're going to discuss in more detail next week. Now, I didn't want to completely leave you with nothing interesting to show for it. So I am going to show you one more thing, which is available if you would like to. Sonia, if you can just tell me once you can see this, please. Perfect. So this will be available for you. We've actually shared this on LinkedIn. What you have here is a very, very simple model, as you can tell, a very simple model, but it's there for a reason, to illustrate the purpose. This is not just a model, but it is a data source. So we've done research on a model, or on the inputs for this model, and we've now created a model. And now we can use this model as the engine to produce data for us using data science techniques, right? And how we do that is we use R. We write a script. That's the computational side of it. And we're going to tell R to look at a sensitivity table, but do a multi-dimensional sensitivity table, which goes beyond just your one-dimensional, or your two-way sensitivity table that you can do in Excel. And the way we do that is we will say, okay, this is our script. We write it up, we standardize it, we click run all cells, and you'll see it will start simulating information for us, like we've done here. And before you know it, it will spit out the final result. and we will have the analytics exactly what we've asked for. So in this instance, we have a sensitivity table. You're looking at the entry yield, the exit yield, the growth rate relative to the IRR, and it gives you all possible iterations from that and also plots the distribution. So here you can start saying, okay, well, on average, if you have to take this on a bit of an average, you're looking at what's that's 0, that's 20. So this is about 10. So you can probably say, what's that, 12 and a half, 13% roughly on average. The distribution is a bit skewed here to the left. You already have information based on just a simple model. And this is hopefully a good indication of what is possible when you know what to do and if you have a strong, robust process. So